Okay, then let's start with the CLO. The statement of the CLO is in front of you. Bismillahirrahmanirrahim. So the statement of the CLO is improve the performance of machine learning models. So improve the performance of models by doing what? By using some metrics and techniques such as confusion matrix and cross validation. Only two metrics are mentioned here, but there are many. Okay, so this is the theoretical part. This is the theoretical part. So in this CLO, we will mostly see the different measures and metrics which are available, which we can use to assess the performance of our models that we have studied in previous CLOs. So we will cover the theoretical part here in this 1.5. And in 2.5, this is here, the practical quiz is already on the blackboard. It will be opened maybe tomorrow. Today is 6, tomorrow it will be opened. So this CLO, when I will give you the practical quiz, then this CLO 2.4, I will assess this CO against this practical quiz. So, okay. So what are evaluation metrics? From your previous course, you already know that what are the evaluation metrics. All these evaluation metrics, you will use them to assess or to test the performance or the effectiveness. You can use only one word or two words, it's up to you. It is theoretical. So you can use only this one word. So we will use these evaluation metrics to assess the performance of the machine learning models. But the question is, which evaluation which we have to use? This question has an answer. The answer of this question depends on your problem. What is your problem? Because not all evaluation metrics are suitable for all problems. So it depends on your problem. It depends on the type of the data that you are using for your model, or what type of output you want to get from your models. So the answer for the selection or the choice of evaluation metric depends on these things. So there are many things. For example, recall is also a measure or metric. Precision is also a measure. auc-roc is also a measure. Confusion matrix, F1 score, loss. These are some of the measures are mentioned, but it is not that limited. It has a limit. You can say not unlimited list, but not limited list like that, which have only 6, 7 measures. No, we have 10, 15, or more than 15 measures existing around us. But we will go with the common evaluation measures. And here first we are going to see the confusion matrix. So confusion matrix is a n by n matrix. You can give any value to this n. For example, if you will give a value to this n5, then it would be 5 cross 5 or 2 cross 2 or whatever. So it is a n cross n matrix. And where n is what? N is the number of the classes that you want to predict. Number of the classes which are existing in your data. So this, if you will build this confusion matrix, then it will be helpful for you to calculate other things. And what are those other things? You can calculate precision. You can calculate recall, specificity, accuracy. Specificity as another name, okay? You will see that. Accuracy, auc-roc curves, sensitivity, and so on and so on. You can calculate all these things from the confusion matrix. But before that, we have to learn some terms so that we can understand what is confusion matrix actually mean. So in the confusion matrix, you will have something which is called true positive, which means your model is predicting positive, which is actually positive in the data set. Okay. Similarly, true negative means your model is predicting negative, which is actually negative in the data set. So that's why I have mentioned you predicted negative. You means your model. Your model predicted negative, and it was the same negative in the data set. That's why I use this word same, only for understanding. Similarly, false positive. The other name for it is type 1 error. So your model predicted it positive, but actually it was opposite negative. Huh? So I mentioned this word opposite. And your model predicted negative, but actually it was opposite, which means positive. This is type 2 error. So you will see these four terms in a confusion matrix soon here. These true positive, false negative, true negative, you will see these. What are the other terms? We learned those four terms. What are the other terms? Accuracy. You know what is accuracy. If 100 are the questions you solved in your final exam and you solved only 80, you are getting 80 out of 100. So the other 20 that either you solved or not, but that is wrong. But total is so 80 out of that is accuracy. Yeah. So that is accuracy. Proportion of the total number of correct predictions that were actually correct. So from that 100, you have given 80 answers correct. And that correction was how we are measuring, because that was correct if the answers are available. Anyhow, that is not a difficult thing. Positive predictive value or precision. These are the two labels, are the two names for the same thing. And the definition for this is proportion of positive cases that were correctly identified. Your model identified them positive and correctly identified. You have to calculate the proportion of that positive, correct positive out of all positive. Correct positive, this is another short version. Correct positive out of all positives. So similarly, negative predicted value, proportion of negative cases, proportion of negative cases. So this negative cases means all negative cases. And what were the correctly identified as negative? And then sensitivity or recall. Recall is what? Proportion of actual positive cases, which are here actually means the cases which are actually available as positive in the data set. And your model also correctly identified it as positive. This is recall. This is recall. So these are just theoretical definitions. If you are not understanding, no issue. When confusion matrix will appear before you, then from those rows and columns, you will understand what is precision, what is recall, what is accuracy. You will understand each and everything. Specificity is what? Proportion of actual negative cases which are correctly identified as negative. And then rate. So rate is what? It is a measuring factor for the confusion matrix, and it has four types: TPR, FPR, TNR, FNR. These are the abbreviation of something. You will see what are those abbreviations. That is not difficult. True positive rate, false positive rate, true negative rate, false negative rate. This is that thing. Now, here we are just presenting a structure of the confusion matrix. On one side, you have a model. On other side, you have a data set. The actual values in your data set. Actual values for what? Actual values for your output. The model, your model. What are the outputs of your model? You have to consider those things in the confusion matrix only. So you can expect that model is predicting your class as positive or model is predicting your class as negative. So this confusion matrix is for a binary classification. One thing, for a binary classification, that either the class can be positive or negative class. There are two classes, positive class or negative class. Spam or not spam. If spam positive, not spam negative. So this is the target, which means actual data that you have in your data set. So the cases are what? The same, positive and negative. And what it means here, the meaning is here that what value you have to write here. If you will write here A, what it means? It means that your model has predicted this as positive and it was actually positive in the data set. In your Excel sheet, you have the data set, huh? And that class was also positive. Similarly here, what is this value for? So it means that your model has predicted it as positive and actually it was negative in the data set. Similarly here, the same reading you can go on. Your model predicted as negative, but it was actually positive in the data set. Your model predicted as negative, but actually it was negative. So negative predicted negative, that is correct, huh? Positive predicted, for example, these two values, positive and model predicted positive, correct. Negative and model predicted it negative, correct. So these things which are in the diagonal, that is something correct answers, correct answers. And these things that you have here, this is the error. It was negative, model predicted is positive. It was positive, model predicted it negative. So now the values that you have here on the in the row, we are calling it positive predicted value or precision. The other name for positive predicted value is what? Precision. In this theory, positive predicted value or precision. So this, so so these things that you are seeing in this row, this is called precision or positive predicted value. And and the equation for that is A divided by A plus B. What this equation is saying? If you have this confusion matrix in your mind, then you will have all the definitions of precision, recall, accuracy, specificity, sensitivity. All definitions are in your mind. What this equation is saying? It is saying A is what? Positive, model predicted also positive. Only correct positive, huh? And then this A plus B, what? This is all positive, predicted positive. This is negative, predicted positive. So your focus is only on the prediction of the model. First thing is, your focus is only on the prediction of the model. Whatever your model is predicted, you are counting only those evidences. You are not counting anything extra. So your model predicted positive to positive, this is that A. And here positive to positive, negative to positive. So you are counting total number of positives which are predicted by your model. Here, total number of positives which are correctly predicted by the model. And this is what? Total number of positives predicted by your model, including correct and false. And false. This is precision. This is precision. And now negative predicted value. That is the same story, but with this row. With this row. D divided by C plus D. So opposite of that one, opposite of this previous one. D is what? D is negative. This was negative, predicted negative. That is here. Opposite of that, huh? And then you have C plus D. So D negative, predicted negative. C is what? Positive, predicted negative. So now you are focusing on negative, which is predicted by your model. Concept is what? Same as you have here. So that's why I'm not explaining it. You can understand it by yourself, huh? I'm just saving my time because there are many things I have to explain next. So now, recall. This column is called recall. The other name is sensitivity. Here, your focus is on the positives that you have. For example, here, for example, the equation is A divided by A plus C. This A that you have is the positives that is correctly identified by your model. But this is divided by A plus C, not A divided by D. And A plus C is what? A is what? Positive, which are predicted positives. And C is what? Positives, but predicted negatives. So now our focus is not on model, our focus is on positives which are existing in the data set, but also predicted somehow positive or incorrect by the model. Huh? Our focus is now shifted. So You can understand these things from the equation. That is not a big, you can say complex science or big science. No, that's easy thing. And then specificity. Here we are focusing on this column, opposite to this one, but we are focusing on only on this column. And the equation is D divided by B plus D. D is this negative, predicted negative. D is what? Negative, predicted negative. And B is what? B was negative, predicted positive, and D is the same. So this equation is the opposite of this equation, nothing else. Here we have a focus on positive column. Here we have a focus on negative column. This is called specificity. And the accuracy is what? This diagonal. I told you, or we already discussed, that positive, predictive, positive, negative, predicted, negative. These are the correct answers. The rest of the entries are false. Huh? So these are the correct. These are your true numbers. Huh? 80 out of 100. Huh? So there you are adding that A plus D, correct answers. Adding. Divided by total number of questions, either correct or false or whatever. Whatever, total number. Yeah. So that is normal accuracy that we are using everywhere. Now this confusion matrix, here we have the values and we have computed these values just only for practice. Here you have two classes, 1 and 0. That is predicted by your model. And then here you have two classes again, 1 and 0, that is available in your data set. Now the values for that is, these are the responses, 3,834 times your model is predicted this class, and 639 times your model is predicted this class 0 as 1. This is what the data means. And then, okay, this row is called positive predicted value or precision, which you are seeing here. And then similarly, this row is negative predicted value, and the value for that you are seeing here. And similarly, you are seeing this value, which is for the sensitivity or the recall. And then similarly, you are seeing this value, 40 by 90, which is the specificity. We calculated this value using this equation. And you can also calculate it using those equations which are written above. Now, so this is accuracy by using this equation. This is only the summation, nothing else. Now, what are the other possibilities that you can calculate? Again, we have now a confusion matrix displayed here. These confusion matrix are very much easy to draw by using your Python code, okay? And here you have one of the samples here. This is your prediction class, which is by the model, and this is your actual class, which is through your data. And then positive, negative, and you have these values for this true positive, false negative, true negative. We already have the understanding of this. This TP, FP, FN, TN, we started with from the first slide with this, first slide of confusion matrix. Now we can calculate the TPR if we have the confusion matrix. And the formula for the TPR is this, TP divided by TP plus FN. Put the values in it from the confusion matrix and you have your answer. Similarly, for FPR, the formula is 1 minus TN divided by TN plus FP. Put the values from here and then you have your answer here. You can also calculate the accuracy through this confusion matrix by using this formula. You can also calculate estimated error rate. And the formula for that is this. If you have calculated accuracy, just put the values and then you have your answer. You can calculate the precision, which has this formula. You can calculate the recall, which has this formula. This formula is repeated because you already have seen in the previous slide, on the previous slide. And you can also calculate F measure through this confusion matrix. And the formula for that is 2 divided by 1 divided by precision plus 1 divided by recall. Put the values of precision and recall that you have calculated already, and then you can calculate it further, and you will have your answer. So, the idea of this slide is you can calculate these different things through this confusion matrix. So that is what we said here. Confusion matrix helps, useful for measuring all these things, etc., which were mentioned there. Now, what is precision? So you know what is the definition of the precision. So that definition is repeated there. I'm not going to repeat it, okay? And the equation for the precision you already know from the previous slide. And this is just an example given to you how you can understand precision. We can read it this. For example, if we are going to detect the spam in the emails, what are the spam emails? Precision will indicate what? What would be the meaning of precision in this example? The meaning would be percentage of correctly identified spam emails. Percentage of correctly identified spam emails, correctly identified by your model, out of all spam mails, out of all spam mails, out of all spam mails. So that is the meaning of the precision. So this is just a repetition. This is just a repetition. I was thinking to remove these slides, but then I said, okay, just I want to remove. But then I said, okay, precision is separate measure also. So that's why this slide is giving you an idea that this is also a separate entity, not the part of the confusion matrix, also a separate. Sometime when you have your model, if you don't want to build a confusion matrix, then you can calculate the precision. And then at least you must have to know the formula for the precision and the recall. Recall is also given here, that formula. Same definition, same equation. Accuracy, same definition, same equation. F measure, same equation, same definition. F measure here, recall inverse. What it means? Recall inverse means 1 over recall. And precision inverse, what it means? 1 over precision. And this whole has inverse. What it means? Just, yeah, just change the position of the numerator and the denominator. 2, then 2 will become the numerator and this will become the denominator. And then you will have this equation which is written here, 2 divided by 1 over precision, 1 over recall. Okay, that is the same story. Now, when the 2 will, now finally this is the equation. Thank you very much. Now the whole semester is gone. Now you are taking care of me. I just have to pause the recording. Okay. So now this is the simplest form of this formula for the F measure. 2 multiplied by precision recall, multiplication of this, and then divided by precision plus recall, divided by summation of these two things. And this, how we can define this? We can say that it is harmonic mean of precision and recall. These are the two things we are multiplying and then dividing. It is what? It is taking like an average. But we are also multiplying it with 2. So it is something different. That thing different is called harmonic mean. For example, you have arithmetic series in mathematics, geometric series, harmonic series is also one thing. So you can study something about the harmonic series and then, but that is not necessary here. But if you want to study, you can study and then you can understand what is harmonic series and then you will understand. So if the value of the F measure can be between 0 and 1, the value of the F measure can be between 0 and 1. If you will have the 0 value, it means the worst value that you have here, the bad value that you. And if you have 1, it means, okay, your model has perfect F measure. It means your model is good, okay? It means your model is good. And how you can get a good F1 score? Some people can also call it F1 score. How you can get a good F1 score? Only if you have a good precision value and only good recall value, then you can expect that you will have a good F1 score. Otherwise, not. F beta measure. The only difference from the previous equation is only that we have the addition of this beta parameter or beta variable or whatever. We have the addition of this beta variable. And now the equation, after addition of this beta, the equation of this F beta measure will become F beta 1 plus beta square multiplied by precision recall, same, precision plus same, but here we are multiplying this precision with the beta square. Now, if you will give this beta the value 1, if you will give this beta the value 1, then 1 plus 1, it will become 2. And this 1 square will become 1. So then the equation will be same as this equation here. If the value of the beta is 1. If the value of the beta is 1, then the equation of this F beta will become same as you have the equation for the F1 score. And if so, it means, and if you will give some smaller value, 0.2, 0.3, 0.4, 0.5, some smaller value to this beta, if you will give some smaller value to this beta, then the weightage of precision in this equation will be higher as compared to recall. And if you will give some higher value like this, 2, 3, 4, like a whole number, then the weightage of recall will be higher. Put these values there and then you will understand how the weightage. When you will divide this equation, then you will see that the precision has more values than the recall. And similarly, recall has more values than the precision. I'm not going to discuss it. You can do it by yourself. But if you will put these values, then you will understand why the weightage to precision is becoming larger than the recall, and why when you have inserted 2, why the weightage to recall has becoming larger than the precision. You can check it by putting the values in it. But one thing is sure from this discussion, that we can play with the value of beta. We can play with the value of beta. So which means that you can tweak the value of beta. You can change the value of beta for your model, and then you can see at which value your model is performing good. And then you will go with that value on which your model is performing good. So anyhow, this is also a measure. And now gain and lift charts. Gain and lift charts, or gain and lift simply. You don't have to say charts. Gain and lift. These are also measures or metrics, you can say. There is a, by the way, difference, minor difference between measure and metrics. But for us, measure and metric is same thing, okay? That is easy to understand. But if you are a student of stat or math, then you have to differentiate it. Gain and lift. Through these measures, we can measure that if we have a model, then, and I am doing some business and I want to develop some model. And then now I want to test, I want to check this, that going with the model is a better approach or without model is a better approach. Running business with a model is a better approach or without model is a better approach. If I want to see the answer of this question, then I can use this gain and lift to find the answer for that. To find the answer for that model would be good for me or not, huh? So this is the purpose. Now you understood that what is the purpose of this gain and lift. So these are the popular measures or techniques which are very much useful in market analysis. You are running a business, You have your market, you are selling your products. You want to analyze something from your sales data. So, so popular in marketing analytics. Anything you want to analyze related to your marketing, then this is good for that. You can also apply this gain and lift in other things. For example, you want to identify the risk or supply chain where your products are supplying. So this is not but popular only in this marketing analysis. Sometime you want to find among models what is the best models among the models which are available to you. If you want to find that, these gain and lift also have the tendency to answer this question. So now moving, so this is just the steps written here, that if you want to perform gain and lift, then these are the steps that you have to do. This is not an algorithm. You can call it algorithm if you want. So, but these are the steps that you have to do. First, you have to split your data into 70 or 30 ratio. 70 is training, 30 is validation or testing, you can say. Then you have to, after this, you have to run your test data on the model. You have to run your 30% data on your model. So score the validation sample using the model. So when you will run this 30% validation sample on your model, then you will have the score for that data. For that data, the model will give you that score, because you want to see that that model is good for me or not, huh? So that score, for example, here, okay, I will come here later on. That is the example. And then after that, then you have to rank the scored file. When you have the scores in your resultant file, then you have to rank that file according to the score or whatever in descending order. In descending order, higher first, lower after. This is a column which is responses in the table next. Here you will see. Here we have 10 deciles. Deciles is like iterative steps, huh? Or divisions that you have done in the test data that you have already run over your model, and now you have that scores. So that file that we are talking here, ranked the scored file, huh? That file, you divided this file into 10 steps, which we are calling it deciles. And each portion, each division is containing 2500 instances, number of cases or events from your data set, And here you equally divided the instances. This is the total of that. And then the number of responses, this is the column here I am talking about. Rank the scored file in descending order. So from 2500 cases, the model has responded positively for 2179 cases. This is the response of the model. For 2500 cases, the model responses for 2179 times for the first decile, you can say. And then, because we have sorted higher first and lower first, so score is already there. So this is the score actually. You can consider this is the score. And by using that score, we are sorting it in descending order. Higher score first, lower score after. This is that step which is mentioned here. Rank the scored file in descending order. And then split the rank file into 10 sections that are the deciles, which we already have splitted here. 10 deciles, huh? So, and then number of observation in each decile, number of cases in each decile. We have already mentioned number of cases in each decile here. In each part, how many total number of cases we have mentioned. So this data will be, you will have this data from the data set. And then The number of actual events in each deciles, number of responses, that is that thing. That is number of actual responses which happened. That is that thing which I was talking about. From this 2500 cases, this is happened by this is positively identified by the model, positively identified for each decile. And then number of cumulative actual events in each decile. The column name is cumulative responses in the table. Cumulative responses in the table. This column, cumulative responses. What is that step? 2179 written here, and then add it to it, and then you will have this number, and then add this number into it, and then you will have this number, and then add this number into it, and then you will have this number. In this way, you are going up to the end. This is called cumulative responses. Now, what is the next? Percentage of cumulative events. Percentage of cumulative actual events in each decile. We are calling it gain score or simply gain. Here, we are here up to this point, and how we are calculating this gain, which is the gain score. I have already drawn the drawings here. So you are using this value to how we are calculating this value. We are using this value divided by this value. Divided by this value. Multiply by 100. And you have this value 44.71. This is okay. Again, look over here. So this value 2179 divided by this value, and you are getting what? This value. And then this value 3932 divided by 4847 multiply by 100, and you are getting this percentage. This percentage. Similarly, how I am getting this value? This value divided by this total multiply by 100, and I am getting this value. So that's why these lines you will see in the slides there, that these lines will give you that idea. So in this way, you are calculating all these values up to the end. Up to the end. And finally, 4874 divided by 4874, it is 1. Multiply by 100, you have 100. Huh? So, but how we are calculating this column, which is the, I can now erase this drawing. But how we are calculating this column, percentage of events, this is a little different from this one, from this gain. So let's have a look over it. So this value 2176, you don't have to focus on this column, okay, for calculating this value. It is this and this is same. So it can create a confusion. So then focus over it. This value divided by this value, and it is giving you this answer. Now, this value 1753 divided by this value total, it is giving you 35.95. Multiply by 100 also, it is also a percentage. And here 396 divided by this, multiply by 100, you are getting this value. So here, these values are the percentages, but you are calculating it for individual responses. Individual, huh? And but these are again the same values, but you are calculating it for this cumulative responses. That is the only difference. That is the only difference. In this way, you can calculate the gain for each decile, for each portion. Now, what is lift, or you can call it cumulative lift? How we are calculating this? How we are calculating this value? 4.47. I have already drawn these lines here. So this value divided by the percentage of this decile. Each decile here is representing 10% of total 100%. Because this is 10, so 10 multiplied by 10 is 100. So each decile is representing 10% portion of the total. So then what? This value, you can multiply it with 10 or you can divide it with 10. And then you will have this answer. You will have this answer. Similarly, this value 80 divided by here you don't have to divide it with 10. Here, now it will become 20. Okay. This is the only difference that you have to take care. For 44, you have to divide it with 10 because it is the first decile. For, for this value, how you will get this value? You will get this value divided by 20, not 10. Okay. And similarly, the third value, this value divided by 30. And similarly, you can go on next, and then you will have your values here in the column. And these are the values for the left. These are the values for the left. Now we will talk about what is gain and what is left. We now know how to calculate the values, but now we will say what is the definition for the gain. That definition is already there on that slide. Gain score and cumulative lift. These are there already, but now you can see these definitions again in a more formal way. So gain is what? It is a ratio of something to something. And what is that first something? Ratio of cumulative events. Ratio of cumulative events. If you are up to that decile, okay, if you are on a decile number 5, then you have to see what is the cumulative events up to that decile 5. And then divided by total number of events. Divided by total number of events in the entire data set. And if you will do that, then you will get the value of gain after division. Or if you are just writing the definition, then you can say it is a ratio of this thing to this thing. I have highlighted those two things, and these two things are given in the table, previously table, and you know how you calculated this gain. This is the cumulative divided by this total. Divided by this total. And if we have a value of gain, for example, this value is interpreting what? This value is interpreting what? It is giving the interpretation is this, that percentage of events percentage of events that you have seen, or that you can say percentage of events your model has seen up to decile 1. Percentage of events your model has seen up to decile 4. This is the interpretation. How you can read this value, huh? Or you can say 96.45% of events are seen by our model at decile 7. This is the reading. How you can take this, how you can read this value. How you can read this value. If you are going to write a thesis, then how you have to write this statement, huh? Yeah. So now that is what it means. And now here we are just, that example is already there, but this example is giving you another idea. What is that? If you will see here in this chart, what this chart is giving an idea. That is the example here. So in this gain chart, number of data sets, 0, 10, 20, 30, 40, number of data sets. You can say the deciles. Huh? Here, this is what? Decile. And then percent of events. Percent of events and number of data sets. So this is what your number of data sets, like that, or this. This is 1, this is then 10, 20, 30, 40, 50, something like that. And number of events is this. It is already there in the table. So you can use these columns and then you can draw that chart by using the Excel, MS Excel or whatever. And suppose if this chart is there, then this chart would be called gain chart. And this diagonal is representing what? Percentage of cumulative events, random. And then this blue line is representing what? Percentage of cumulative events, model. And I am using those two columns which are given in the table, in the previous table that you already have seen. I am using that and we are drawing this chart by using MS Excel simply. And here we are seeing that so here we have covered 10% of the data set, 20% of the data set, 30% of the data set. And we have seen when the data set is 20%, then what was this blue is what? Percentage of cumulative events that was seen by the model. This random means manual. You can do it by yourself, checking on every decile. But this model means you are checking on the model. And this blue line is by the model. So when you have covered 20% of the data, you have covered what? 80% of the events from your data set. From your set. This is the interpretation of this chart. Or in other way, by covering only 20% of the customers, you are actually covering 80%. Or you can say by covering only 20% of the data, you are actually covering 80% of the customers, feedback or whatever you want to say. So here, 80% of events covered in top 20% of data. This chart is saying based on this example. So this model is giving you this option that if you will cover only 20% of data, then it will cover at almost what? 80% of customers who want to buy some product or whatever, huh? So this is a good thing that you can adopt. So from this, this is also a point that we should have to go for this model. We should have to go for this model. This line which is going in the diagonal, which is random. Random means manual. When you are doing your manual work, that is that trend. That is that trend. When you were selecting data set randomly, and then you were selecting you were selecting that these customers will buy the product or not, also randomly, and it was a linear relation. But when you will go with this model and by using this gain chart, you have seen that if you will go with that model, then after covering this 20% of data set, you are covering actually 80% of the customer. And these are those customers, which means that they are going to buy the product. And maybe you will send only email to 20% of the customers and then they will come and buy. Huh? This is another option. You don't have to do too much marketing. Huh? You will send an email to this 20% of this email, 20% of the customers. And then you will cover almost 80% of the customers. Anyhow, this is the advantage of gain. Moving next. What is left? This is the definition. Ratio. This definition, we are writing it here by observing that table that we already have seen. So this is the ratio of the what? Gain. This is the ratio of the gain percent to the random percent at a given decile. Let's say, so for example, if I will remove all this drawing, how I am getting this lift? How I am getting this value? From the gain. It is a ratio of the gain divided by this percentage of decile. percentage of each decile has a percentage. For example, first has 10, second has 20, 30, 40, something like that. That is that thing mentioned there. Yes. So that's why it is mentioned ratio of the gain percent, ratio of the gain percent to the random percenter at a given decile. And how you can get this percentage of a given decile? It is also mentioned here that the random percent at x decile, for example, it is second decile, then it would be 20%. If it is 1, then it would be 10%. If it is 3, then it would be 30%. This is what it means. This is what it means. And this lift will measure what? Measure the advantage of going with the model or without model. Again, the same. We started the story with this. With this question, we started the story that either we want to go with the model or not. So this measure is again, this lift will also measure that either we should have to go with the model or not. And this is the lift chart. Number of data set, it is same. First 10% decile, 20%, 30%. This is decile, data set. And then the values of the lift, 0 up to going up to 5. It can go beyond 5, okay? This is not fixed values. Lift will have some positive value. So starting from 0 up to any limit. But it would be something like that. So if you have higher value for the lift, higher means, for example, here, the data that you have here, higher values, higher than 1 at least, I'm just saying, just an estimate, then it means that that thing is good. That thing, that model is, for example, good. From this example, here we have the lift values 4.47 and 4.03, which are the highest, among all these. What these values are saying. So that lift of 4.03, 4.03 is at the second row of that table. 4.03 is at the second row of the table, second decile. So when we have this is cumulative lift. After 2 deciles, we have this value 4.03. What it means? It means the same. When our model has seen 20% of the data, and if the value is 4.03, what it means? It means that you will cover 4 times the total number of events. That 4.03 means, just for the sake of ease, I am using only the 4. Otherwise, you can say, what it means that after the model has seen only 20% of the data set, and this, by looking at the 20% of the data set, this is equal to 4 times the total number of events from the data set. It is equal to what? That it has seen 4 times the number of events found. As compared to what? As compared to random selection. Random selection means manual. If you have seen your data set 20% manually, which is this line, each time it has the same value. For 10%, the lift is 1. For 20, the lift will remain same for the random. But if now you have that model, through that model you have those values, you calculated those values in that table, and in that table you have the values for the lift, and you have the values for the data set. You draw this chart, which is called lift chart, and here you can see this blue line is for the lift. This is also for the lift, but random. And that 4.03, and then the values are decreasing. So what is the meaning? The meaning is that that you have seen only 20% of the data, and the value is 4.03, which is this point, which means that you have seen 4 times more total number of events as compared to this manual approach. As compared to this manual approach. This is what this chart is saying. But anyhow, this measure will give you the same advantage as the advantage you try to get from the gain measure. Now, another measure, Kolmogorov Smirnov chart. So Kolmogorov Smirnov chart. This is a Russian name or Soviet Union name or something like that. So this person has given its own measure for measuring the degree of separation between positive and negative distribution. If you have two classes, positive and negative, how that classes are distributed in this data set, this measure will measure that separation. This measure will measure the degree that how that those classes are separated from each other. And through, for example, here, is it visible? This table. And here you can see, then this is one class which is represented with 0. This is another class which is represented with 1. You can consider it positive, negative, huh? And then, okay, these are your 10 deciles or whatever. And then here for the first, this class is not predicted, but this class 1 is predicted 543 times. Similarly, for the second decile, so the zeroth class is predicted 2 times, class 1 is predicted 542 times. And this is the meaning of these two columns, huh? And now, okay, grand total is just summing these values, and then you have these values, okay? Now, how we are calculating this percentage of rights? Rights mean this, maybe this class 1, which is positive class, huh? So this is not needed. You can leave this. This is not needed. This is a mistake here, huh? And then the values are starting from here actually. And then how we are getting this percentage of rights? 543 divided by this total number, you are getting this. Similarly, now the next one, 542 divided by this multiplied by 100, you are getting this percentage. Similarly, 573 divided by this multiplied by 100, you are getting this. So the value would be real value. That would be close to 14%. Okay. So that's why you are getting 14 again and again. Sometime you will get 13.9. When you will round it, it will become 14. Huh? So this is how we are getting the values for this column here. And similarly, percentage of wrongs. This is wrongs for 0. This value divided by this value multiplied by 100, you are getting this value. Then this value divided by this multiplied by 100, you are getting this value. Then this value divided by this multiplied by 100, you are getting this value. Then this value divided by this, now 15 is a little bit prominent. Divide by that and multiply by 100, you will get this value. And in this way, you are getting these values. Okay. Maybe you are using round here, okay? And after that, now, if I will remove this drawing, now how we are getting these cumulatives? Cumulative percentage of right. Okay, this is cumulative percentage of this right class and cumulative percentage of this wrong class. That is easy, 0. So, okay, leave this first because this is just an error. So now here, how I am getting this first, for the first entry, okay, I am getting this 14. Then This 14 plus this 14, I am getting 28. Cumulative. This 28 plus this 14, I am getting 42. And you are getting the values like that. Hmm? You are just adding and you are getting the cumulative values like that. Similar approach with the percentage of this wrong, and then you have these values here. And now after that, simply the difference between that. So difference between that, 14 minus this, you will have this. This minus this, you will have this. This minus this, you will have this. Simply difference. You can either you can use these actual values and then you can find the difference, because somewhere you will have different value. For example, where is that? 83, 77, that is okay. 69 minus 3, it is 66, but you have 67 here. Why 67? Because you are calculating this difference using the actual values here, not the values here that you have here. Here we have rounded values. You are using actual real values, huh? So that is the reason that you have this minor difference. So when you are calculating all these differences, then you will, so this is that KS value. This is that Kolmogorov Smirnov value. And then from all these values, you will have some cell that will have the highest values. And this is that cell which has the highest value. This is that cell which has the highest value. What it means? What it means? This is that meaning. You know, this is the wrong and this is the right. So you will draw the chart between, I am removing that drawing. You will draw a chart between right and wrong, and you will see something like that. And then you will have your KS82. What is that value? That is the gap between these two, maximum gap. This is KS, which is 82, which is representing that what is the distance between the good and the bad, or the right and wrong class. These are the two classes. And this gap is 82. This gap is KS. This is the degree which this KS is measuring, that with this maximum degree, these two classes are separated. And this is what we said here, that this measure will measure what? It will measure the degree of separation between the two classes. And now, if you will have your KS value 100, then what it means? It means that your model has partitioned the two classes completely. This is the meaning. If the KS is 100, and if KS is 0, it means that your model is not able, or your model fails to differentiate the two classes completely when your KS is 0. And then what you can do? Then you can do the random decision, manual approach. Okay. Then you can do what? Then you can do random decision if your KS value is 0. And if your KS value is between 0 and 100, if your value is higher like this, it is not 100, but it is higher, then it means that your model is able to separate these two classes with that percentage, 82%. And it is separating the positive class better as compared to the negative class, as you are seeing here. This is what this measure means. Now, moving to this auc-roc curve. What is this auc-roc? This auc means area under the curve, and this roc means receiver operating characteristics. Auc means area under the curve, and roc means receiver operating characteristics curve. So what is this auc-roc? This is a graphical representation, as you are seeing here. And through this graphical representation, we can see the performance of a binary classification model. We can see the performance of a binary classification model by supplying it various thresholds. You will you will check the model on by giving different threshold. By setting the different thresholds, you can check the performance of your model. And through this auc-roc, and auc-roc is what? It is a graphical representation. It is a graphical representation like you are seeing here, but this is not the actual representation. Here, this rock curve is what? This is again a graphical representation between TPR and FPR. If you will see what is this rock, if this is rock, then this is between FPR and TPR. On x-axis you have FPR, on y-axis you have TPR. And then you can draw this curve. This is called rock, and this diagonal is called auc. But this area of auc lies between what? 0 and 1. Lies between what? 0 and 1. 0 and 1. Due to this FPR and TPR, because FPR and TPR values are between 0 and 1. Okay. Because the values of FPR and TPR are the probability values. So it would be between 0 and 1. So then this auc curve will also have the values between 0 and 1. And if you have higher value or greater value of this auc, it means your model is performing better. And our goal here in the auc, our goal here is to maximize this area, by having highest TPR, okay, at this point we have the highest TPR and lowest FPR. So anyhow, now we will see this auc-roc in detail. But before that, these are the terms that are needed to understand this auc-roc. These terms include recall. We already know what is recall. The other name for the recall is TPR or sensitivity. And the equation for the TPR is given here. We already seen this equation somewhere, TPR. If I will go back, here we have seen what is TPR and what is FPR. We already seen it on this slide number 8. So that's why I'm not going to discuss it in detail, and that's why it is mentioned here. Read it by yourself. What is FPR? This is the equation for that. What is specificity? This is the equation for that. It is already given there. So we will use these equations. So these are the terms used is auc-roc, which we already know what are these terms. Now, moving slowly towards the example of auc-roc. And here on this slide, we have mentioned that what is the relationship between these different terms, TPR, TNR, and threshold. For example, here, sensitivity and specificity, what is the relationship? And we are saying there is an inverse relationship between these two terms. If one is higher, the other will be lower. And if that would be higher, the other will be lower. You will see some theoretical statements here. You will see some statements like that here, which will show only the relationship between these terms. The only thing needed is to read this. And then you will understand. You have to keep this, that this is the relationship between the different terms. So that's why it is mentioned here. Read it by yourself just to save my time. So I am moving next. Now, how does this auc-roc work? Now, we are now going to start the example which will involve some calculation, but this calculation would be simple calculation, not too much. It would be lengthy, but it would not be a complex thing. So how does this auc-roc work? If the question is, For example, if this is the question, what an arc of 0.7 would actually mean? Then what is the meaning of that? So it means that the model is able, it means that the model has 75% of chance, you can say, or the model is able, 75% the model is able to separate the two classes completely. To separate or segregate the two classes completely. This is what it means. I have highlighted what is the meaning of that. So if you have the awk value 0.75, then what it actually means? It means that the model has 75% chance to separate the two classes or to order them correctly. Or you can say that here positive class has higher probability than the negative class. You can also say something like that. That positive point has a higher prediction probability than the negative class. Let's see through this example and then we will move towards our calculation. Here in this example, we have 6 points, 6 data points, P1, P2, P3, P4, P5, P6. We have 6 data points. Because in this, what we said here, what is the awk of this 0.75 means? And here we said that, okay, assume 2 data points or 2 classes. Assume 2 data points belonging to separate classes. And then there is a 70% chance for this model that this model will separate or segregate these 2 points completely or separate these 2 classes completely. Now, to understand it further, we are taking this example with 6 points, P1, P2, P3, P4. And these points are related to which class? It is mentioned that P1 is related to class 1, P2 has the class 1, P3 is the data point of class 0, P5 has the class 1, P6 has the class 0, related to class 0. And what are their probabilities? That is also mentioned. P1 has the probability 0.95 with this class, P2 has 0.90 with this class, 0.85 with this 0 with this class. This is what the meaning of this column is. Now, so now we have 3 points, P2, this P1, P2 and P5. These are 3 points which are related to class 1. And then we have other 3 points which are related to class 0. Probabilities are also given. And now, if some person will give me any 2 points from here, from these 6 points, if some person will give me any 2 points from here, then what is the probability that the model will rank or will order or will separate it correctly? Now the question is, if these are the 2 subsets, according to this example, probability values are also given. And if some person will give me 2 points from here randomly, and then the question is, what is the probability that the model will rank these 2 points correctly or will deal these 2 points correctly? Now, this is the question. And for this, you have to do what? To answer this question, you have to do what? You have to make all the possible pairs first. So that's why you have to make what? You have to make all possible pairs of these 2 groups first. One group is what? P1, P2, P5. This is one group. Other group is what? P3, P4, P6. This is for the class 0. This is for the class 1. So you have to do what? You have to build pairs. How you can make pairs? P1 with P3, P1 with P4, P1 with P6. And then again, P1 with P3, P2 with P4, P2 with P6. And then again for the same P5. This is how you are making all these pairs here, possible pairs from those two subsets. P1, P3, P1, P4, P1 with all, P2 with all, P5 with all. And now, by looking at their probability values, here, P1 has the higher probability or the P3 has the higher probability? P1 has the higher probability or the P3 has the higher probability? P1 has the higher probability. If P1 is higher, then okay, is it correct? Is this, we can write yes or no. That the first is if the first point in this pair has the higher probability, then you can write yes here. And if the first point has not the higher probability, then you can write no there. Okay. So that data is repeated here. And now P1, P3. If you will see, this is P1, this is P3. So the first one is higher, yes. Now check this one, P2, P4. P2, 90, P4 is 81, 90 is higher. So, okay, yes. Check this P5, P3. P5 is this, P3 is what? P5 is this, P3 is what? This. First is not higher. First is lower, huh? When lower, we are writing no. Because we are writing what? Low. Because the other class is predicted. You can say this is first class, yes is first class, no is other class, huh? You can also consider like that. So now, if you will count, then 7 are the yeses and 2 are the no's, and total entries are 9. Total entries are 9 in this table. 7 are what? 7 are for the class 1. So we can say 7 out of 9 possible pairs, and class 1 is ranked higher than class 0. Class 0 means no, class 1 means yes. And 7 out of 9 multiplied by 100, you will have 77%. So then 77% chance that if you will pick any pair from it, then your model would be able to distinguish them correctly. Then 77% chance that your model will, if you will give any pair, then 77% chance that your model will predict it correctly. This is the answer of this question here. This is the answer of this question here. So this question has the answer ended here up to this point. But this is not finished yet. This was only the answer of that previous question. Now, the question is, when we have to use this auc-roc? What are the situations where I have to use this auc-roc? If your data is imbalanced, then you don't have to use auc-roc, okay? Because if your data is imbalanced, then it is quite possible that you have many points there which is false for that class, but your model will predict it positive. So if your data is highly imbalanced, then, and if you are using auc-roc, then this auc-roc measure will give you overly optimistic results. Then, or you can say, then this, if the data is imbalanced and you are using this auc-roc and you are getting the visualization through this auc-roc, what will happen? It will give you overly optimistic performance of the model. What it means? Like, for example, some person can be overconfident, huh? The same approach is. This is the same meaning here. The auc-roc will give you overconfident results that were actually not, huh? It will give you the positive results in large quantity, but actually that were not, because your data is imbalanced. And when your data is imbalanced, then normally FPR is very small, because in your data you have actual negative, the number of actual negative instances large. You have large number of actual negative instances there. which your model is predicting positive, but actually they are negative. So what you have to do, if your data is imbalanced, you don't have to use this. In this situation, you can go only with the precision recall curve. If you want to draw a curve, you can use precision here, recall here, and then you can draw the curve if you want. But auc-roc for imbalanced data is not a good option. It is only good for balanced data set. Now, what we can speculate from the values of that auc-roc? When we have a value of auc close to 1, like 0.75 that you have seen previously, then it means that your model is excellent discriminator. Your model is excellent in separating the two classes or two data points, or in excellent in discriminating or differentiating these two classes. And if your auc value is close to 0, this is the opposite of that one. Poor discriminatory behavior of your model. Poor discriminatory behavior of your model. And if your values are around 0.5 or 0.5 simply, then it means it is 50-50. You can say it is 50-50, and your model is doing what? It is just throwing the values randomly. It is just throwing the values randomly. Your model has not learned anything from the data during its training phase, not learned anything. And it is just throwing what? The decisions 50-50, which means randomly, just throwing sometime yes, sometime no, whatever. Anyhow, this is what you can understand through the values of that auc-roc. Now, we have that proper example for that auc-roc, which is taking almost 3-4 slides. This is not complex, that is easy, but it is repetitive. If we have an auc-roc curve, we know that in the auc-roc, on the x-axis, we have this FPR, and on the y-axis, we have this TPR. If I will go back to this is FPR, this is TPR. And now, this is what we know that. And anyhow, this is just a definition. Now we have an example that how the auc-roc curves can be generated for different thresholds, and how a particular threshold correspond to the confusion matrix. This is now the question. The question is how we can generate the auc-roc curves for different thresholds. We will change different thresholds and we will get different auc-rocs. And how for different thresholds, the values in the confusion matrix will change. This is the question now. How we can answer this question? First, we have to suppose some model. So that's why we are supposing some binary classification model. That is for the spam mean positive or negative, you can say. And then we are supposing some data to start the calculation. And here we are supposing some data, which that's why it is written here, hypothetical data, true labels. True label means this class is, this is the data point for class 1. This is the data point for the class 2. This is the data point for the class 1 and 2, 1, 1, 0, 0, and so on. This is what it means. And their probabilities for these data points, here the probability value is 0.8. For this, the probability value is 0.3. For this, the prob value is, I will say prob. Okay? Because I am feeling difficult in probability again and again. It is coming onto my tongue. So then prob. So this 1 has this 0.6, this 0 has 0.2, and so on. So this data you can assume by yourself, or it would be given to you. Now, The question was how we can generate this auc-roc curve. We have to generate auc-roc curve visually. So how we can generate this auc-roc curve? By using different thresholds. Okay, we have assumed this data, and then here we are assuming that case 1, and we are taking our threshold is 0.5 randomly. We are saying that our threshold is 5. These true labels were given in the previous slides, 1 0 1 0. This is the same story. And these probability values which are written here, we are using these probability values here in this column. Prediction label. Now, this prediction label is different. This is you have to calculate. Prediction labels. If the threshold is 5, what is mean? If the probability value is 5 or less, this is class 0. And if the probability value is higher than 0.5, this is class 1. So this is 0.1, so class is 1. This is 0.3, class is 0. This is 0.6, class is 1. 0.2, class is 0. By looking at these values, you can identify these labels. So this is prediction labels, okay? Prediction labels. You can assume that your model is working over it, okay? But you are doing this manual calculation by yourself, but actually your model will do. Anyhow, so this is what? Now you will create a confusion matrix. And this is how you can create a confusion matrix. Actual value, actual class in your data set, predicted by your model, predicted class by your model, and the classes are 0, 1, 0, 1, as we mentioned here, 0, 1, 0, 1. In our data, we have the classes 0, 1, 0, 1. This prediction is by your model, and this is your data set. Now, you have to count what? TP means what? When your actual is 0 and your model predicted 0. When your actual is 0 and your model predicted 0. When your actual is 0, your model predicted 0. When your actual is 0, model predicted 0. When your actual 0, model predicted 0. How many entries? 4. That 4 is written here. You have to count these. And now here, your actual class was 0, but model predicted 1. Actual class 0, I will remove that. Actual class 0, model predicted 1, not this, not this, not this, not this, this one. Actual 0, predicted 1, only one count. So you can calculate these values like that, okay? And now your confusion matrix is ready. And you know what is TP, what is FP. Now, if you know the formula for TPR and FPR, put these values by using this confusion matrix, put these values in the formula. You have the value for the TPR, and put these values by using this confusion matrix in this FPR, and you have this value. And now, what is the meaning of these values? Now that interpretation is here. The meaning is that at this threshold 0.5, the model correctly identifies 80% of actual positives as positive. 80%. This is what model predicted positive, which are actually positive. Model predicted positive, which are actually negative. This FP means I'm giving you the definition of that FP. So then what? At this threshold, the model correctly identifies 80% of the actual positives as positives and 0% of actual negatives. This was actual negatives as positive. This is FPR. This is the interpretation. Now you will change the threshold. Now you will, case 2, you will change the threshold. Threshold is now 0.7. What it means? If the probability value is 0.7 or less, is it class 0? If it is higher than that, class 1. So by using that approach, this is class 1, This is 0, this is 0, this is 0, this is 0, not higher. Not higher, so that's why. This is 1, this is 0, this is 0. By looking at this threshold, you are seeing that. And then you are calculating that confusion matrix by using that same approach. By using that same approach. Actual zero, predicted zero. Okay, these are the total actual zeros entries, huh? Actual zeros, predicted zero. This is predicted zero, 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 0, 0, 5, huh? 5. So by using that same approach, you have this confusion matrix. Put in the formulas of TPR and FPR. Point 1, point 2. Interpretation. At this threshold of 0.7, the model correctly identified 100%. Okay, this one means 100% of actual positives as positive. And similarly, 20% of actual negatives as positive. As positive. Now, change the threshold again. Why we are changing it again? Because we want to draw the curve. For that curve, you at least need 5, 6, 7 points. Okay, 5, 6, 7 points. So now you change the threshold. So that's up to now you have only got 2 points, and now you will get another point. You change the threshold, and you know what is the meaning of that threshold by applying the same concept here. You got the confusion matrix by using the same approach. Then you have the TPR and FPR, and then the interpretation. Same. Then here, case 4, now you are done. You are going to take the threshold too. I'm not showing you the tables. You will calculate by yourself, okay? And I am just writing the answers. You will get the TPR, this TPR, and this FPR. I'm not showing you this, not showing you this. So you will get the TPR 0.4 for this threshold and FPR this for that threshold. Similarly, now in case 5, you will take the threshold 0.85, and then you will get TPR and FPR like this. Now at least we have 5 points. Now we can draw that auc-roc curve. How you can use that? The code is here. The true positive rate, TPR, whatever the values you got here at different thresholds, I'm writing all those values here. One is this 0.4, 0.8, 2 times, 1.0 or 1. This is 1.0, 1.0, okay? So all the values that you got here you can say 0.8 2 times. And this is 1.0. And 1.0 how many times? 2 times. 2 times. So all those values written, the order is changed, but values are the same, okay? You can write in any order. And this FPR, these values that you, FPR are these values that you obtained here, which you are writing it here. And now you are giving it into the Python code, and then this code is displaying that auc-roc curve for you. So this is the diagonal, and by using these values, it is displaying that roc curve for that auc-roc curve. This is the worst case. You know that this diagonal is normally representing the random approach. This is FPR values, these are TPR values, and it is displaying that auc-roc curve simply. Now, so here in this graph, this dashed line, this is the diagonal, which is a random approach. This is the worst approach, huh? And here, this blue, this is the auc-roc curve, or you can shortly say roc curve here. So this gray dashed line represents worst case. Why worst case? Because TPR and FPR values would be same there, random approach. And when the points are deviating from here, when the points started drawn here, from the top left corner and going like that, then this curve will show the improvements, the improvement for your model. Here you don't have any improvement. This is the worst performance. But when you will have the curve like that, up higher than this diagonal, up higher than this diagonal, and the shape is like that, it is something okay. Your model has starting some improvement from this maybe 0.001, and then it is suddenly go to point 4, which is the TPR, which means what? Po- Identifying positive, which are actually positive. So that is also the definition is there. And then it is going like that, and then suddenly it has further improvement. When you are increasing so increase in FPR and also increase in TPR goes like that, this curve will show that you have improvement, your improvement is started, and this is the overall performance. This is the overall performance. This is what I mentioned here. This is what I mentioned here in sentences. We know that when the auc-roc value is close to 1, it means we already discussed, it means close to 1, it means excellent discriminator, huh? So that thing is again the same thing here. If your value is close to 1, it means your model is has the best, has the close to 1 means, for example, zero point 0.8, zero point 0.9, something like that. It means your model has some better performance. And if your value is exactly 1, then it means it has 100% sensitivity, 100% specificity. This is extra narrations, you can say. I am just describing what this means, what this means. But the actual calculation you have already done on the previous slides. Now, the whole discussion that you have done here, it is for the binary classification. And for example, if you have to use this auc-roc for multi-class, then what you have to do? For multi-class, if you have to do this for multi-class, then what you have to do? You have to then use this one versus all methodology. I will, after this slide, I will stop. Then we will offer prayer and then we will start again, okay? So if we have multi-classes, not a binary, we don't have a binary classifier. If we are going to do something with the multi-classifier, then, and if we want to use auc-roc, then what we have to do? We have to use this methodology, which is called one versus all methodology. What it means? It means, for example, if you have 4 classes, A, B, C, D, you will take one class out from that 4 classes. You will take one class out. For example, A, you are taking it out and you are calling it one class. And the all other B, C, D, you are calling it all, huh? The remaining all. And similarly, and then you will do some training or you will do something. And then in the second iteration, you will take B class out and then you will call it one. And the remaining, you will combine them and you will call them all. And in the next, you will take C out and you will combine the remaining. And then in the next, you will take D out and you will combine the remaining. This is called one versus all methodology. Here, its execution is mentioned in words that for each, for example, if you have 4 classes, then for each class, you have to do what? You have to treat it positive. The one class that you will take out, you will consider it positive. And the remaining that you have put in a combination, you will consider them negative classes or simply a negative class. Okay. And then you have to do what? You have to train like a binary classifier. You have to train it like a binary classifier. And you will do that again and again for each class until you have taken all the classes at least one time out. Okay. Not at least, exactly one time out. So this is one step. And here in this picture, if you will see this graph here, we have taken 4 classes. This diagonal is the random guess, and we have taken logistic regression as a binary classifier. And then we have taken random forest as a binary classifier. Logistic regression is represented with this brown color. Random forest, execution of this random forest is represented here with this blue color. It is just a picture to give you an idea. When you have taken class A out and all combined, and you have run it over random sample, you have this line. When you have taken B out and all combined over random sample, you again have this same line. When you have taken C out on a random sample, you again have the same line. Now, by using the logistic regression, or first with the random forest has these blue curves. You have taken A out, remaining combined, A is positive, remaining is negative, and if you draw the curve, you have one curve like that. Next, you have taken B out, remaining combined, positive, negative, and then you have drawn the auc-roc, you have one auc-roc like that. And similarly, for the next C class, here we are not considering D or something. We are considering only A, B, C. Huh? And then here, similarly, when now you are using logistic regression, and then you are taking A out, remaining combined, and then you have this auc-roc, one curve, which is representing for the A, then representation for the B, and then representation for the C. And this is how you are checking these two classifiers, logistic regression and random forest. You are first checking the auc-roc, and this chart is giving you an idea that logistic regression has performed well than the random forest by using the one versus all methodology for multi-classification, and by using the auc-roc measure. Because these brown curves are in a better position, at a better altitude, you can say. This is what written here, and this is read it by yourself, log loss, Gini coefficient, read it by yourself, concordant, read it by yourself, RMSC, read it by yourself. Equation is simple, okay, that is not difficult. These are simple things. And I will start from here after the break. It will take maybe 20 minutes or something like that. So first we have a break and then we will come back. Okay, now let's start. What is cross validation? So this is very famous technique mostly people are using. So in this technique, whatever the data set you have to divide your data set into subsets, or you can call it simply folds. And then you will take one fold out. That one fold that you will take out, you will call it test data or validation data, and the others is your training data. And then you will get the training of your model on this division. And then you will repeat this process. You will take another fold or subset out, and on the remaining, remaining would be the training, and then you will get the training of the model again. And then you will keep on doing this until you have all folds taken as a test data. So this is what the cross validation is called. And then the other step that you can do is for one fold, which you have taken as test result, you have the result 1. Then for second fold, you have the result 2. Third fold, you have the result 3, and so on, up to the last. Then you will just take an average of those results. That result would be more accurate and more authentic result as compared to some other measures. So normally we use this cross validation for overfitting, and you know the definition of overfitting, because we have seen what is overfitting and underfitting in the beginning. To reduce this, to prevent this overfitting, we normally use this measure of cross validation. And what are the types of it? Normally 4 divisions, 4 types, you can say 4 divisions. And the selection of these divisions or selection of this type depend again on the size and nature of the data, the problem. You have only 3, 4 words which you can throw, huh? Which you can throw. So again, that choice is depending on the size and nature of the data or any specific requirement of the problem. But what are the 4 types? Starting with one, holdout data. In the holdout data, you will divide your data set into 2 halves. Okay, into 2 halves, 50%, 50%. 50% would be training, 50% would be your test data or validation data. And then you will train your model. And there is no repetition needed because it is 50%. So 50%. So there is no repetition. So you will do the training only for once. So this is called, what is his name? Hold out validation. But the major drawback is that you are dividing into 2 halves. And then when you will get the training of the model, it is possible that some important information is missing in the training data. That would be the part of the test data. So that is the major drawback which is written here. Then second is leave one out cross validation. Leave one out cross. Again, leave one out. You have to take one out from the data set. So you will do what? You will train your model on the complete data set, but you will take one data point out. Okay, one data point out. That would not be the part of that training. So that is one iteration, and then in the next iteration you will take another data point out, and then you will get the training of the whole model again. And then you will take another point, data point number 3 out, and yet you will get the training of the remaining whole data, or you will get the training of your model on the remaining whole data. And in this way, you will do that up until you have all the data points covered. So this one thing is, working on data points is not a good approach. If your data set has less number of points, only then you can select this one. Otherwise, it is not a good measure. It is not a good measure to work on data points and keeping the whole data set aside. If the size of the data set is small, then you can go for that. Otherwise, it's not a good measure. But if you will go with this approach, one data point and whole data set, as you are considering almost the whole data set there, 99.9%, then the biasness is low. The biasness that you will feel there on the point number 1, where you have the drawback is what? Drawback, important information is missing. That is one category of biasness. So that is for when the important information is missing from the training data. That is one drawback, which is, you can call it, your data is biased. Your data is biased to some aspect, and that aspect is missing information in the training data. But here, if you will do something like that, you are considering whole data. So the biasness is no biasness is there. Or you can simply say low biased. So this is the advantage. But what can be the disadvantage? If you are working on data points, so if your data point is an outlier, outlier is something at a distance from your data. So then your model will be fail on these outlier. Then your model will be fail, and you will have high variation in your visualization or in your results or whatever. So this is the second type or category. And similarly, the third category is the stratified cross validation. In this category, you will again divide your data set into k folds, but you will take care of one thing. And what is that thing? You will keep the same proportion of each class in these k folds. For example, you have designed 10 folds, and then you will do what? And if in your data set, the number of the classes is 2, binary classification, then you will keep the data of each class with equal proportion in each of these k folds. Okay. So this is the condition now. This is the condition. This is the condition now. And due to this condition, it is different from this next k-fold cross validation, which is general without any condition. But this is due to this condition, it is called stratified class cross validation. And you can do this only when your data is, if your data set is imbalanced, if your data set is imbalanced. And in these situations, this stratified cross validation would be a good option for you, because then you can explicitly or manually, you can put the proportion of the class that you want to predict in the k folds. You will shift the data manually, and then you are balancing, actually you are balancing it. So then in this situation, this approach is better. And now the fourth one is k-fold cross validation. Again, you have a data set, you will divide your data set into k number of folds. This k can be 5, can be 10, can be 20, whatever. You will take what? You will take one fold out of this k. So you are calling it and k minus 1 or whatever. And then you will get the training of your model. And then in the next iteration, you will take another fold out, and then you will get the training. And then in the next iteration, you will get another fold out, and you will get the training. So this is the normal k-fold cross validation, which we talked about in the definition. Okay, in the definition, whatever we talked, we were talking about this k-fold cross validation. So that is the normal. That is the normal. And you have to do this until you have covered all the folds. Now, this is just an example. This is visual example that here we have this data to understand k-fold cross validation. This is just a visual interpretation that this is your data set. Now you divided this data set into maybe 80% training, 20% test data. And then, okay, you have taken this part of the data. So this is one fold. And this is that one fold. And now in the next fold, you are leaving this part of the data set and you are taking the next part of the data as a test data. And then this is the second fold. And then in the next, you are leaving that previous part, you are taking this part. So you are moving it physically. And this picture is giving you an idea that you are now considering now the next 20%, next 20%, next 20%. This is the first 20%. This is the next 20%. This is the next 20%. This is the next 20%. And this is the next 20%. This is fold 1, fold 2, fold 3, fold 5, 4, and fold 5. So, and similarly, what is this picture is showing? In this picture, your data set has 25 instances. 25 total examples are instances. And here, if the value of k is 5, then what would be the number of iterations? In the first iteration, the training set would be like that. Because you have taken the first 5, because number of k is what? 5. And you are doing what? From this 25, you 0, 1, 2, 3, and 4. This is the first test data, you can say. And which is starting from 0, which is taking examples from 0 to 4, 5 examples. And then the remaining from 5 to 45, these instances are in the training data. This is for the first fold or first iteration. Then in the second, according to this picture, it's the same idea. And in the second picture, now you are taking the data from 5 up to 9 as a test data. And then the remaining, and this is not the part of this, that is the training data. And in the third, from 10 to 14, because 9 is already done. So 10 to 14, this is your training test data, and the remaining is what? the training data. And in this way, you are covering k folds, five-fold, which is five folds. The theoretical description of these numbers are written here. This is just a theoretical description that this diagram below shows an example of five folds cross validation having 25 instances initially. First iteration, 20% of the data, which is this one, 20% of the data, which is from 0 to 4 for evaluation or test data, and the remaining 80% from 5 to 24, which is mentioned here. And similarly, second iteration, third iteration, and so on. This is an example for that. And finally, you have this source code. This source code is using some libraries. And then here, this is an array for representing actual data. Actual data means, okay, this is class one, this is class one, dog, and then not dog, dog, not dog. So these are the values for the classes, your actual data. And then your model, for example, your model has predicted these values, dog, not dog, dog, not dog. So this is the prediction results of your model, and this is the actual data in the data set. And here, confusion matrix, you are giving actual and predicted these arrays into it, and this, and logically confusion matrix is drawn in the memory, huh? So and you have this cm, and then now you are setting this cm. Okay, you are taking x tick labels dog not dog like that, and y tick labels, this is what dog log. So you are just setting the values of x labels and y, and prediction at y label. So this prediction you are showing actual at x labels, this actual confusion matrix at title, this is you are showing. And then finally you are showing this plot dot show, and here this confusion matrix is displayed by using this actual and predicted values there. These values, it is automatically counting what are the values which are taking dog and dog, for example, and dog and predicted by dog. And these numbers that you have here automatically calculating this confusion matrix which you are using a pre-built function. And similarly, print classification report, you are giving actual and predicted classification report. And then it is automatically calculating precision, recall, F1 score, support. And with these classes, dog and not dog, it is showing you these values of precision, recall, F score, support. Also giving you the accuracy values, and similarly macro average, weighted average. So this classification report is giving you that whole report. This is the end, and this is the end of the CLO.